Yes, thanks.
That's nice.
Yep, so
Okay.
you have 20 minutes.
Yeah, so this is my 20 minutes. As I said, this is me, this is our work. And first of all, I'd like to introduce the team. That was me. I have a PhD degree and I work in Kazan Federal University. Also, big part of this work has been done by Denis Porplenko from Ukrainian Catholic University. And also some work on the manuscripts has been done by Elena Tutubalina, PhD, also from Kazan Federal University. I should acknowledge the help of RFBR. You see project numbers there. And also, we as a team are really grateful to Sports.ru administration, which provided us with the corpus. The corpus will be released, but unfortunately we're not in charge of the releasing the corpus itself. This is on their side. Okay, so first of all, the dataset itself. I need to introduce the concept of text broadcast. If you ever have seen it, I don't know if you have tried to not watch but read the translation of some sport event, for example, soccer match or I don't know, hockey match, something like this, hockey game. Then the idea there is that there is at least one person, maybe several persons, several people who look at the picture, or maybe they're there on the stadium and they're writing some comments during the game, and these comments are broadcasted on, for example, sports site. So we have almost 9,000 text broadcasts with 700,000 utterances in them. So the example here is like, good day, our site congratulates everyone who counted the days before the start of the Russian Premier League. Our first text broadcast will help you follow the events that will take, and so on. So this is the first few utterances of sample broadcast, and the typical broadcast is about 1,000 utterances. Actually, a little bit less, but this is not really important. So this is text broadcast. It is actually a huge document, and we have some issues with these documents, working with them, but I'll be addressing this in a few minutes. This dataset also contains news documents which are associated with this text broadcast. So there are almost 93,000 of news, and that means that each game has actually several several news which are accompanying the game or text translation in our case, and this news actually could be divided in several different groups, like for example the news which came before the game but they also related to the game, the news which are came after the game, so they are obviously related to the game, and news actually could address several events in the game, or maybe they could address the whole game, like analyzing its results or something like this. The example of the last type of the news is presented here. Real Madrid won in the 22nd round of the Championship of Spain against Real Sociedad. 4-1 and led his winning streak in home games this season to 11 matches. Jose Mourinho's pupils in the current championship have been lost a single point in Santiago Bernabeu. The winning series of Real in the home walls of the example has already been 14 meetings. Goal ratio is 41-9 in favor to the Royal Club. So this is, as I said, the analysis of the whole game of Real Madrid with Real Sociedad. And we actually, in our work, we are concentrating on the news which came after the game. So there are some news which came before the games, but we are not addressing them in this work. This could be the future work. Okay, so I have presented you the dataset itself. Now I'll be presenting the summarization task. This summarization task is divided roughly into two different approaches. This is extractive summarization, and this is abstractive summarization. The extractive summarization one is actually, we get the document, we split this document to the sentences or maybe smaller phrases, and we're choosing from this set of sentences which sentences are actually the best ones which represent the main idea of the text, so we call them summary. And for abstractive summarization, we actually generate a summary. So we read with a model a document, and we reformulate the sentences into the shorter version of this text. So we use maybe the whole text in some approaches, not the whole text, but we use the original document in some way, and we generate a new text. Actually, human summaries in the most cases are reformulating the original text. Okay, so the extractive summarization, as I said, this is we take some sentences or phrases, and there are actually approaches to this extractive summarization task, which are supervised and unsupervised. The supervised approach includes the gold markup of the phrases which have been taken into the golden summary, and the unsupervised approach is that does not include such markup, doesn't require it. So in our case, we have no such markup, so we have specialized only the unsupervised approaches. They are the most common ones, actually, in my experience. So the extractive approaches are mostly could be represented by this scheme. So we have some text. This text is split into sentences. These sentences are vectorized. We compute the similarity matrix. We think of this similarity matrix as a graph. So since the similarity matrix is obviously symmetric, we could use only, for example, the higher triangle matrix, and we think of the values in the cells as the weights on the edges of this graph, while the column numbers and row numbers are the nodes themselves. Okay, so after that, we're computing some specific ranking. For example, it could be the most the node with the most incoming edges is the most important one on something like this, and this sentences, since the sentences are ranked, we just get the top, for example, 20% of the sentences, and they are actually our ranking. Sorry, our summary. So the almost all of the known to me extractive approaches are actually using this scheme, and we have experimented with TextRank, the most classical one approach, I think, LexRank, with more relied on the lexical similarity, and to our own implementations of PageRank. The first one is relying on word2vec, and the second one is relying on fast text. Oh, I'm sorry, I need to explain how the TextRank is doing the vectorization. It uses TF-IDF, or in some modifications BM25, but in our modification it was TF-IDF. In the PageRank, we have averaging the word2vec vectors of words to actually produce sentence embedding, or fast text embedding to produce the sentence one. Okay, the abstractive summarization, as I said, it is common that we have some bigger text and we reformulate it to the smaller text, which are supposed to be summaries. There are also supervised and unsupervised approaches, but in our case, we have supervised signal. So we have the text translation itself, and we have news, which we suppose to be summary of the text translation. And we actually concentrated on the supervised approaches only. So a few words of the background of this work. This is transformer. I think nowadays really few natural language processing research works could say that they do not use transformer, but we do. So this is work from Vasvani and others from 2017. This is approach of using only attention, a specific type of attention mechanism with feedforward to actually produce the output for any sec-to-sec task. I'll be not actually spending more time on that, and I'll be going to the next slide. The abstractive approaches we have been using, they have been developed by the Mirella Lapata and her student, I think, a year ago. And this is so-called BERT-sum apps. BERT-sum apps, this is, first of all, what is the BERT for summarization? BERT is using transformer. It is using the embedding of the tokens. This is actually not words themselves, but for simplicity, they are words. The words and special tokens, and also positional embedding. And the important part is the so-called context embedding, or the part embedding, I think it is called. So we're embedding the part A with one vector and embedding part B with another vector. And so the model can actually know that these are the different different models, different sentences. And after that, the whole embedding, which is the sum of these three types of embedding, is fed to the transformer layers, and these transformer layers are actually outputting the embeddings. This is the BERT for summarization. This is actually, I would say, a small small modification, but the BERT sum ups. It is used BERT for summarization as the encoder. So the encoder is just reading the text and outputting the set of the vectors. And this set of the vectors is then fed into transformer output, the 6-layer transformer output, which is producing the output word by word. So this is classical sec-to-sec task. So this is called BERT sum ups. The other approach, which is called BERT sum ext ups, it is using a bit other approach. It is using that it is using for fine-tuning on the extractive summarization task at first, and then the abstractive summarization. So this approach is actually improving the BERT sum abs results on the abstractive summarization task. So that was the architecture of these two models. We also used what we actually have been using. The BERT sum ups we have been using with multilingual BERT. We also used ROUGE-BERT from Deep Pavlov for BERT sum ups, and we call this model ROUGE-BERT sum ups. We used BERT sum ext ups with again multilingual BERT, and we extended this extended this model with greater context. The original model uses only 512 input tokens, and we extended this to the 1024 tokens as input. As I said, the broadcast, they are really long, could be, and we need more context to actually get something, but you see everything on the results page. This is actually not all the abstractive approaches we have been has tried. Also, we have tried BERT sum ext ups clean, so-called, which is extension of the previous BERT sum ext ups model with additional cleaning of the data. So there is specific technical data in the text broadcast and the news. For example, in many news, there are several technical information, technical sentences. For example, the place, time, the previous some previous background, or something like this. In the text broadcast, there are tables, there are some technical info which is regarding to the exact translation. There are some images also, and we have removed this technical info thoroughly, and this also have shown some improvement. We also have tried the augmentation for the BERT ups model. We have been augmenting the text translation using Russian distributional thesaurus. So we have been replacing some words with a probability of 1/10 with their synonyms according to the Russian distributional thesaurus. And also we have done the same with replacement from word-to-vec similarity. We have word-to-vec model from the project of Rus Victoras. And we have been replacing some words with the most similar one from the according to this model. Okay, so we have been used ROUGE as metric. There are actually several ROUGE metrics, which is mm, which depends on the number of n-grams we have been using. I mean the length of n-gram we have been using. So we're just counting matching n-grams and dividing it by the all n-grams. Also, there is so-called ROUGE-L variant of the ROUGE metric, which is using mm, the longest common subsequence, and this is ROUGE-L. And actually, this classical definition defines only the precision. Oh, I'm sorry, only recall. Also, we could define precision and F-measure like in other like in classic F-measure metric, and we use all these metrics. So this is ROUGE-1 precision, recall F-measure, and so on for the ROUGE-2 and ROUGE-L. So I have skipped the Oracle models we have been using because Oracle may be not the best idea to discuss it with such details. This is a model which has access to the actual gold summaries, and it knows which the which are the best summaries are, and mm, the results are presented here. So Oracle is the at the top. The page rank, text rank, and links rank are lower, and they show, I would say, not really great, not really great results. I think this is due to the specificality of our task, which is really hard for these models. There are models for the which is based on BERT sum up, so they are abstractive. As you can see, for some reason, multilingual BERT is almost everywhere better than the ROUGE-BERT based model. I don't know the exact answer why it is so. The exact, I'm sorry, extractive abstractive model shows lower results. Despite that, on the English level, on the English dataset in the original work, they have been presenting the improvement. After we have extended the context, the model has shown some improvement over the abstractive model. The cleaning have not been shown the best, the improvement for some reason. The best model here is augmented model, which is trained on the augmented dataset with Thesaurus. But the Word-to-Vec is also improving all the results, but the best results are achieved by the augmented model with Thesaurus. Also, we have done the human evaluation, where we asked if 5 annotators to actually say if this summary is relevant or not, consistent or not, fluent or not, and coherent or not. And as you can see, the best results shown by the Oracle, which is actually not really surprising, because Oracle is actually knows the best results. But interestingly, the best results have been achieved by these metrics. I mean, have been achieved for the relevance and consistency for BERT sum ext abs long, and by the fluency and coherence by BERT sum abs clean. That could be explained that cleaned model is has no this technical data which could broke the fluency and coherence of the abstractive summarization. This is our hypothesis. Okay, so this is the conclusion. We have presented a new summarization dataset in Russian, and I would say this dataset is unique and has no analogs in other languages. We have presented actually many baselines, more than 10 baselines, which have been showing different approaches on this dataset. Now we know that augmentation helps. This is also not a surprise, but we tried and improved our results with it. And we could surpass the Oracle, even though the Oracle itself knows the truth. But when we have really good model, we could actually train it to be better than Oracle. This is actually also not results. Also not surprise. There are some works which are also showing that, but we have shown that at least for Russian. Okay, so thank you for your attention. I'm open for your questions.
Yeah, thanks, Valentin. So we have time for maybe one very quick question. Anyone?
Hello, can you hear me?
Yeah.
Yeah, my name is Daniel, and I have a question about the results. So I was confused to see that, well, unigram overlap was about 20%, and bigram overlap was, well, about 2%. Yes, if I recall correctly. Well, for Oracle, and this is actually a strange behavior. Is these well, summaries are too abstractive, or it's really hard to, well, build them?
So thank you for your question. This is actually due to the specifics of our dataset. We're using the news document as a summary. So since this is news document, it has a really small bigram intersection between the original text translation and the news document. This is just the specifics of the dataset. So like that. I hope that dataset will be available maybe in a few weeks, and you could have a look on the data by yourself.
Thank you.
Yeah, of course.